of all, question about the makeup class. Because we need to make up 2 classes, right? I missed one this week actually, and one last time. How we are going to design final exam questions. Okay, so I'll talk about how we do final exam later, not today. Any questions? No? Okay, all right. Let's continue from last time, all right? So. Oh, the final project, yes. So the final project will be due about 2 weeks after the, actually 1 week after the final exam date. Right. So that's, so the final exam will be on, hold on. So the final exam, let's go back to January, right? So the final exam will be on the 7th, which is like February this year, right? Okay, so it will be on the 7th. So we have 1 more week after that. So probably I'll make the final project due on the 15th, or 14th or 15th. So that gave me a couple of days for me to submit the grades. Now, in the summer, they gave me about 4 weeks to submit the grades. So I was very happy I could make everybody, I could make the due date really late. But for winter vacation, unfortunately, because it's short, they really want us to submit the grades within 2 weeks. So really, there's nothing more I can do about this. All right. So everybody, the due date will be sometime around the 15th. Okay. Let's do that. And I was trying to submit the grades before the end of the 2nd week after finals. Okay. Yeah. So if you have any questions about final project, or you want more detailed instructions, or you want to discuss with me what you want to do, you probably need to. So we only have about slightly over 1 month from now, right? So 1 month, 5 weeks from now. So it's time to start worrying about your final project. And if you have any questions, you want to discuss what you want to do, talk to me, okay? Anytime, send me a message or something. Okay, so let's continue from last time, all right? Now, last time we were talking about potential outcome framework. Just to remind everybody what potential outcome is. For any x, which we call a treatment, right? So the treatment can be a binary, the treatment can be anything, but in the most simplistic way, we consider x equal to 0, 1, which is our treatment. And the potential outcome framework, think about the y as potentially belonging to one of the 2 random variables. So y is, we have a y0 and y1, right? 2 counterfactual outcomes, or 2 potential outcomes. Now, depending on which treatment we receive, whether we receive 0 or 1, we observe one of them, right? So one of them becomes the realized outcome. So maybe this one, and this is the realized outcome, and this one becomes the counterfactual, right? Counterfactual. So in this case, this is treatment x, and we have potential outcome y0 and y1. And so depending on what x is, if x is actually 0, then what we observe is y0. So y0 is the realized outcome, and y1 is the potential or counterfactual outcome. Now if x is 1, then y0 becomes the counterfactual, and y1 becomes the realized. Right? So that's the conceptual framework of the potential outcome framework. Okay, so now we define causal effect in the potential outcome framework, or the Rubin causal model, this is called. How do we define causal effect? Well, we define causal effect as any time the distribution of y0 is not equal to the distribution of y1. If under the treatment of 0 versus under treatment of 1, these 2 potential outcomes have different distribution, we say x has a causal effect on y, right? Okay, so here x only has 2 values, 0, 1. So under 2 different values of x, we have different potential outcomes. We say x has a causal effect on y. But how do we actually summarize that causal effect? We need some kind of summary measure. And the summary measure typically used is called ATE, the average treatment effect, which is the expectation of y1 minus y0. All right? Okay, so that's the ATE. Now we can also talk about 2 other treatment effects. So the average treatment effect, so the ATE stands for average treatment effect. Okay? Now the word treatment effect is actually causal effect. The same thing. The reason why we call them treatment effect is because, like I said last time, the Rubin causal model uses the language of experiments to describe causation. Right? You don't have to, but That's their choice, right? They choose to use the language of experimentation. That's why they call things like treatment effect, which is actually the causal effect. Very interesting. All right. Now, what is the AT? The AT turned out to be, we can write it this way. We can write the AT as EY1 minus EY0 conditional on x equal to 1. Okay? Probability times the probability of x. Sorry. Times the probability of x equal to 1 plus e y1 minus y0 conditional on x equal to 0, p x equal to 0. I can write this simple decomposition, right? Okay, which give me two things. Now this is the causal effect of x on y, conditional on x equal to 1. What does conditional on x equal to 1 means? It means the population in which the people receive the treatment of x equal to 1, right? Okay, think about there's a population, right? There are many people. Okay, so there's a person here, there's a person, right? So there are many people here. So these people receive x equal to 1. All right? Now, these people receive x equal to 0. In the language of experimentation, in the language of experiments, we say these people, sometimes we say these people are the control group. These people are the treatment group. Okay? That's a typical language from experiments. Now, what is this? This is the causal effect among the people who end up receiving x equal to 1. In other words, this is the causal effect in this group, okay? In this group of people. All right? Okay. So this is the causal effect among these people, because these people are the people who receive x equal to 1, which is this conditional mean, right? What does this conditional mean? This conditional, when we say conditional on x equal to 1, we mean we're trying to find out the expectation within this group, okay? Within the group of people who receive x equal to 1. So that is what this is. And we have a name for this. This is called ATT. It's called average treatment effect on the treated. Because we think about x equal to 1 in this case as the treated. And we can think about these people as the people who are not treated, right? They're x equal to 0. They're not treated, okay? So this is average treatment effect on the treated. What about these people? What is this, right? Now this is the causal effect on people who receive x equal to 0, which is these people, okay? So this is the causal effect among these people. And I call it ATU, the average treatment effect among the people who are not treated, untreated, okay? So the U stands for untreated. Right? So the ATE is a combination of ATT and ATU, right? So it's the treatment effect on the treated versus treatment effect on the untreated. That's one way to decompose the ATT. All right, so in other words, to find out ATE, one way to do this, one way to find out ATE is to find out what ATT and ATU is, right? So once we know ATU and ATT, we know ATE, all right? So let's try and find a way to compute ATT and ATU. Okay, how do we do that? Well, let's try. Okay, so what is ATT? Average treatment among the treated. Well, the ATT is y1 minus y0 conditional on x equal to 1. The question is, can we compute that? Okay. Well, we know that this is just equal to what? y1 conditional on x equal to 1 minus ey0 conditional on x equal to 1. Okay? So, what is this? This is the expectation of y1 conditional on x equal to 1. I'm going to say that for this one, I can simply write it as ey given x equal to 1. Do people see why I can write this way? So what is the y1? y1 is the potential outcome if the person receives treatment x equal to 1. Now, what is this? This is conditional on people who actually receive x equal to 1. So, for people who actually receive x equal to 1, their y, their realized y, is y1, right? Do people follow this logic? So let's let's go back to take a look at this table, right? Take a look at this table, right? So these are the people who actually receive x equal to 1. Now, for these people, there are two potential outcomes, y0 and y1. But because they actually receive x equal to 1, we only see y1, right? So in other words, their realized outcome, the observed outcome y, is equal to y1 for these people. For these people, they realize the observed outcome y is equal to y0 because they receive x equal to 0. Okay? So if we only look at people who receive x equal to 1, which is this, what this conditional mean, right? When we conditional x equal to 1, we are only looking at people who receive x equal to 1. In that case, their y, their observed outcome y, is exactly equivalent to their potential outcome y1. Do people follow this logic? Okay? Right. So if we only look at people who receive x equal to 1, then their observed outcome y is y1. Is the potential outcome. Right. Now similarly, if we only look at people who receive x equal to 0, if we only look at people who receive x equal to 0, then their outcome, their observed outcome y, is exactly equal to y0, right? Okay. So in that case, we say we can write EY is equivalent to EY0 conditional x equal to 0 because they are the same thing. All right, they're the same thing. Okay, so this is basically equal to EY conditional x equal to 1. Now, question: can I estimate this from data? Yes, right? Because in the data, I see x, I see y. This y is the observed outcome, right? So I see y, I see x. I can estimate it from data. Now, what about this one? This one is the potential outcome if they receive x equal to 0. But in reality, they receive x equal to 1, right? So that's what this conditional expectation means. It means that in reality, these people receive x equal to 1. But we want to know what is the expectation of y if they have received x equal to 0. So this is the expectation of a counterfactual outcome, because this y0 has not happened, because in reality they receive x equal to 1. So can we estimate this from data? In general, no, right? In general, no. Because we do not see this, right? We do not see y0. We only see y1 when x equal to 1. Okay? So how do we estimate the counterfactual outcome? One way to think about causal inference is we want to find out the counterfactual outcome. That's it. That's what it is. Okay. So one way to think about causal inference, majority causal inference, is the goal of causal inference is to find out what would happen if we apply a different kind of treatment than the one they actually receive. This inference about a counterfactual, you can think about it as one of the major points of doing causal inference. So our difficulty for causal inference is to find out this one, not this one. This is easy, right? Now this is the hard part, okay? Because we actually do not see y0 in reality. Right. So similarly, you can use the same logic. You can say for ATU, it's the same story. For ATU, we observe which one? Which one do we observe? We observe the expectation of y0 conditional x equal to 0. Because when x equal to 0, the y is y0. But we do not see this one. We do not see y1. So again, there's a counterfactual we do not know. If we know them, then we can figure out AT. It's very easy, right? AT is the sum of both components. All right, so how do we get this one? How do we get x versus y0? Well, it turns out that one of the simplest way to get it is to what? Is to do this. Okay. So that's let me ask you a question, right? If I tell you that that the x, suppose I tell you that there's a random variable called y, and suppose I tell you, okay, so y equal to 0 equal to ey. Suppose I give you just two random variables, any two random variables, right? Y, x and y, two random variables. And I tell you that, look, the expectation of y conditional, let me change it to p, okay? The probability. So the probability of y conditional x equal to 1 is exactly the same as probability of y equal to x conditional x equal to 0, and exactly the same as probability of 1. If I tell you this, what can you tell me about xy? What can you tell me about them? They're independent, right? Okay, very good. Xy independent. If xy are independent, then I have this very nice property, right? Okay, so let's come back. I want to figure out this thing, right? ey0 conditional x equal to 1. Now, what if I make x and y0? Remember, y0 is a random variable. Okay, so we have three random variables. We have x, y0, and y1. You can think about, in the potential outcome framework, in the Rubin causal model, you can think about the underlying random variable as these three random variables. And realize, what is the observed y? Observed y is one of them, right? So we can say, okay, observed y is equivalent to y0 times if I x equal to 0 plus y1 times I x equal to 1. I can write it this way, right? Okay, it's one of them. So in other words, the observed y is a function. It's a function of these three variables: x, y0, y1. It's a function. So we observe x as a function of these three variables. But underlying the observed y and x, we have these three fundamental variables: x, y0, y1. That is according to the Rubin causal model. We have these three fundamental variables. So y0 is a random variable, y1 is a random variable, x is a random variable. What if I make x and y0 independent? What happens? If these two are independent, then I can write what? I can write ey0 conditional on x equal to 0. They should be the same, right? They're independent. But look, what is y0? What is y0 when x equal to 0? It is just equal to what? Ey conditional x to 0, right? Because when x equal to 0, y is basically y0. Right? So if they're independent, if I can make these two independent, then I can write this whole thing as ey conditional x equal to 0, and I can estimate this from data. Right? Okay. So in other words, in order to estimate this thing from data, one thing to do is to make the x and the y0 independent. How do I make x and the y0 independent? That's the question, right? Can I make x independent from y0 and y1, right? Because they're symmetric. So can I make x and y0, y1 completely independent? Well, the answer is yes, we can. And the simplest way to do that is to what? Now, think about what does independence mean, right? It means that the potential outcome of y under x equal to 1, under x equal to 0 have nothing to do with the actual treatment they receive. So my potential outcome has nothing to do with the treatment I receive. I will not receive x equal to 1 because my y1 is higher. I will not receive x equal to 0 because my y0 is lower or something, right? So the treatment I receive have nothing to do with my potential outcome. How do you guarantee that? You do what? Sorry? Yeah, but how do you make x completely independent from your potential outcome? How do you guarantee that the treatment that somebody receives have nothing to do with the potential outcome that person? Random experiments. Okay, it's really simple. If we randomly assign treatment to people, just close your eyes, right? Just randomly assign. So you get 1, you get 0, you get 1, you get 0. Then in that case, the treatment will be completely random, right? And have nothing to do with their potential outcome. Okay, so that's why randomization works. If you randomly assign the x to people, then the x will be independent from anything, okay, from the potential outcome of these people. And in that case, x will be independent from y0 and y1. And if that's the case, then we can directly compute this part from this part. Okay. Really, that's it. Right. So that's how randomization works. The randomization guarantees, in the potential outcome framework, randomization guarantees that the treatment x becomes independent of the potential outcome. And if that's true, if that's the case, then we can write E y1 minus y0, okay? Now if we do randomization, then we can write this thing as if we can make x independent of y0 and y1, make it independent of these two random variables, because x is completely random assigned, not correlated with any anybody's potential outcome. Then we can write it this way. We can write ey1 given minus ey0 is simply equal to ey1 minus ey0, right? I can always write this way. But what is ey1? ey1 is equivalent to ey1 conditional on x equal to 1, correct? Because they are independent now. X and y are independent. So I can write it this way, but if I write it this way, this is simply equal to ey conditional x equal, which is estimated from data, right? You can estimate from data. Now similarly, I can write it this way. So basically, the conditional expectation of y conditional x is equal to 1 minus the expectation of y conditional x to 0 becomes the causal effect. If you look at this part, what is this part? This part is the average outcome among people who receive treatment equal to 1. This part is the average outcome among people who receive treatment x equal to 0, right? Or in the control group. So what this is saying is that you simply compare people who are in the treatment group versus people who are in the control group. The difference is the causal effect. There's nothing you need to worry about. The difference tells you causal effect. This is true if x is randomized, okay? If x is randomly assigned. That's the case. This is what randomization or randomized experiment can do for us. All right. Now, if the x is not randomized, then we don't have this property, okay? We can no longer do this, which I will talk about very shortly. But so that brings us. By the way, so for people who are unfamiliar with this idea of talking about conditional expectation versus versus unconditional expectation. So here's a nice way to understand the discussion we just had, which is this. The EY conditional x equal to 1 is the average outcome among the people who have received treatment x equal to 1. And if x is randomly assigned, then this is equal to EY1. But how do we actually understand EY1? The EY1, remember, when we say expectation, it is always with regard to an underlying population. Okay? So there's always an underlying population. And we're taking the expectation on that population. So let's think about there's all these people in the population. What EY1 means is suppose we give everybody the treatment of x equal to 1. So suppose everybody receive x equal to 1. Right? And then their outcome will be y1, right? And then we take the expectation. So the EY1 is the expected outcome if everybody in the population receive x equal to 1. Do people follow that? What about this? What about EY conditional x equal to 1? Now, in reality, not everybody receive x equal to 1. In reality, only these people, okay, only person here, like only these people, suppose only these people receive x equal to 1. So these are the treatment group, okay? These are the people who receive x equal to 1. So EY conditional x equal to 1 is the average outcome in this group, which is a subpopulation, okay? It's not the entire population, it's a subpopulation. It's the population that actually receive x equal to 1. But EY1 is the entire population. It's a counterfactual question, right? We're asking a counterfactual question, which is if the entire population, everybody, receive x equal to 1, what is the average mean outcome. That is what EY1 is. Right. So one way to think about this is, okay, if we are comparing, so if we're comparing EY1 minus EY0, what we're doing is we have an underlying population like this. And EY1 is if the entire population receive x equal to 1. EY0 is if the entire population receive x equal to 0. And we compute their mean difference. That is EY1 minus EY0. And that is the causal effect. Okay, that is a causal effect, right? Okay. What is this one? This is the expected outcome in a subpopulation. Not the entire population, but a subpopulation. The subpopulation of people who actually receive x equal to 1. Okay? So in other words, EY conditional x equal to 1 is the average y among the people who actually receive x equal to 1, minus the expectation y among the people who actually receive x equal to 0, which is also a subpopulation. So we're comparing the average outcome in one subpopulation versus the average outcome in another subpopulation. Right. Now, without randomization, these two can be different. But with randomization effects, these two are exactly the same if we computed mean difference. So think about why. Right? Think about why. So first of all, do people get this picture, right? I hope people get this picture of why this is the case. Okay? One is when you're conditional on something, we're only looking at something within the subpopulation. When we do counterfactuals, when you say, why given the treatment x1, when doing a counterfactual, we're assuming the entire population can get it. Okay. So, when will this be different from this? Okay. When are they different? And when are they the same? Remember, EY conditional x equal to 1 is the mean y within this population. Okay? And EY1 is the mean y if everybody receives x to 1 within the large population. When are they different? If I tell you that this population is basically the same, so the people here in this population is almost the same as people here in people here. In other words, the large population just like the small population, then they should be the same, right? When are they different? When this population looks very different from the people here, right? Okay, so if the population here are very different, then these two will be very different. But if the population are almost exactly the same people, then they should be the same. Okay? Right? Okay? So the key here, to guarantee that this one and this one looks the same, the key is to guarantee that the people the people who actually receive treatment x equal to 1 look almost exactly like the people who do not receive x equal to 1. If you can guarantee that, then they should be very much the same. Okay? So think about in reality what this means. And think about why randomization helps. There are two different questions. In reality, what this means is, suppose I suppose I give you everybody a treatment, right? So I say, okay, if I give you a treatment of taking this test A versus the test B, and I say the test A is difficult, the test A is more difficult, the test B is easier, and I want to say what is the difficult test what is the impact on you guys, right? Okay, so there are two ways to do it. One way is I ask you to volunteer. Who wants to take the difficult test? And who wants to take the easier test? So those who volunteer to take the difficult test will be here. Those who volunteer to take the easier test will be here. If I compute the average grade of the people who receive the difficult test, I'm getting this one, okay? EY conditional x equal. Okay? And this average grade, would this average grade be very similar to the average grade if I force everybody to take the difficult test? If I force everybody to take a difficult test, we're computing this one. Okay? When are they different and when are they the same? So the average grade, if I force everybody to take the difficult test, we're having this one. If I ask some of you to take the difficult test, we're taking this one. So when are they almost the same? If the people who take the difficult test are almost the same as the people who do not take the difficult test, right? So how do we guarantee that? If I ask you to volunteer, if I say, oh, who wants to take a difficult test? And some people who volunteer for that, are those people going to be the same as people who volunteer not to take it? They are going to be different, right? Okay. In particular, I should expect that people who volunteer to take the difficult test probably are more capable than people who do not, right? So in other words, they too will be very different. Okay? However, if I randomly pick 50% of you to take the difficult test, then I should expect that the people who take the test versus people who do not take the test are almost exactly the same. In that case, these two are the same, right? So in other words, in order to write this causal effect in terms of this, we need to randomly assign x. That's again the lesson. If we randomly assign x, then the people who take x equal to 1 are almost exactly like the people who do not take that. And I can write this one. So that's the power of randomization, which is guaranteed that the people who receive different values of treatment are almost exactly the same. The reason why without randomization this doesn't work is because people who take different treatment tend to be very different in reality if you do not randomize. People who take the difficult test are different from people who take the easy test. People who go to college are very different from people who do not go to college. Everything else, right, are not equal. In that case, you cannot simply compare the average outcome among different group of people. Right? So that doesn't tell you the true causal effect. It's really that simple, the idea. Okay? Right. Now, if you think about independence, it's the same story. So by randomly assign difficult tests to you, some of you, I make sure that suppose everybody has a potential outcome. Okay? So for people, so if you take the difficult, everybody, right? If you take the difficult test, this might be your score. If you take the easy test, this might be your score. Okay? So for some people who are more capable, they have a higher score if they take the difficult test. That's the potential outcome. For some people who are less capable, their potential outcome of x of y1 is lower. So if I ask you to volunteer to take the test, then those who volunteer to take the difficult test, these people tend to have a higher y1. So their potential outcome of taking the difficult test will be better than people who do not volunteer. In this case, in other words, the assignment of x become correlated with the potential outcome. People who have better potential outcome of the difficult test will volunteer to receive x equal to 1. So the assignment x is now not independent from the potential outcome. But if I randomly give the test to you, then x become independent from the potential outcome. So that's another way to understand how we are able to write this. All right? Okay. Now, like I said, without randomization, the simple formula I have just written does not work. Okay? So with randomization, I can simply write the average treatment effect is simply equal to EY conditional x equal to 1 minus EY conditional x equal to 2. It's extremely simple. We can estimate this from data. Simply compare people who receive treatment versus people who do not receive treatment. Tell us the causal effect. But without randomization, this is no longer true. All right? In particular, now without randomization, okay, there are two things that can lead to a bias. So what the so-called bias. Let's again take a look at the difficult test problem, right? The difficult test problem, I can write it this way. Without randomization, what happens? So without randomization, I can say, like EY1, so let's write it this way, okay? EY conditional x equal to 1 minus EY conditional x to 0, which is I compare the test of people who receive the difficult test versus the grades of people who do not receive the difficult test. The easy test is equal to EY conditional x equal to 1 minus EY0 conditional x equal to 1, okay, plus EY0 conditional equal to 1 minus EY conditional x to 0. Let me just do a little bit of algebra, all right? Minus this plus this, nothing else changes. Okay. The question is this equal to EY1 minus EY0? The answer is without randomization, this is not true. So we're not getting causal effect. This is the causal effect we want. But without randomization, it's not true. We don't get it. Without randomization, in general, we can write it this way. I'm simply minus this and plus this here. But let's look at this part. Okay? What is this part? This part is the average y among people who receive the difficult test versus the grade among those people who receive the difficult test versus their grade if they had received the easy test. Right? Okay? So this is the observed grade. This is the grade if they had received the easy test. So what is this? This is the ATT. Do people see that? What is ATT? ATT is the average causal effect among people who actually receive the treatment, x equal to 1. The ATT is defined as EY1 minus Y0 conditional on x equal to 1. That's the definition. Do people see that they're exactly the same thing? Because when x equal to 1, our observed y is equal to y1, right? Okay, so they're the same thing. So this is ATT. That's great. But what about this part? What is this part? Well, this part is the people who do not receive the difficult test. The people who receive the easy test, their grade, right? What about this one? This one is the people who receive the difficult test. Their grade if they had received the easy test. This is the grade of people who actually received the easy test. So this is like a comparing, so this is asking, suppose, for these people, suppose you guys receive the difficult test, you guys the easy test. This is asking, what will your guys' grade be if I give you the easy test? And let's compare this with the actual grade of these people. All right? Do you expect this to be positive or negative if the X is not randomly assigned? If I let people volunteer. Suppose I say, okay, anybody volunteer for the difficult test. These people volunteer, these people do not volunteer. And I'm going to compare these people's grade if they had received the easy test versus the actual grade of these people. Do you think they'll be positive or negative? Any answers? Why? Because they tend to be more capable, right? So people who volunteer tend to be more capable people. So if they're more capable, and if I give them the actual easy test, they will score higher than these people, right? Okay, so they tend to be positive than 0. What do we call this in economics? You have a word that you're all very familiar with. This is called self-selection effect. Have people heard about this? Self-selection, right? So self-selection effect means, in reality, people choose X themselves. They are not randomly assigned. They are chosen by people themselves. And how do people choose? Well, people who are more capable will choose to take the difficult test, or people more capable will choose to go to college. So people people who are better at something will choose to do that something. So it is, or people who are sicker choose to go to hospital, right? So people choose based on their potential outcome, if you will. And because people choose, then this is larger than this is larger than 0. This is called self-selection effect. And because of the existence of self-selection effect, we do not get this, okay? We do not get a causal effect from EY x1 minus EY 0. All right? Okay? Again, with randomization, if we have randomization, then these three are actually the same. AT equal to ATT equal to AT. With randomization, all these three are the same. And they're all equal to EY condition x1 minus EY condition x equal to 0. Right? Why? Let's take a look at ATT's definition. Okay? Every treatment effect is just EY1 minus EY0. ATT is EY1 minus EY0 conditional x to 1. The other is conditional x to 0. But under randomization, when we have randomization, people who receive x equal to 1 look just like the people who receive x to 0. And look just like the other people, underlying population. So they're all the same. Okay? Under randomization, these effects are all the same because people are all the same who receive x equal 1 versus equal to 0. Doesn't matter, right? So they're all the same. But once we do not have randomization, once x is not randomly assigned, we have this self-selection effect, which is this is ATE is no longer equal to ATT because this part is larger than 0. So now we have a self-selection effect going on. And dealing with self-selection effect is the key issue with economics. Okay? Because in economics, we study social science, and in social science, people make their choice themselves. So the treatment people receive in economics are typically not randomized. They're typically self-chosen. And when self-chosen, we have the self-selection effect, which is permeate, rampant, right? Which is everywhere in economics. So you can say the self-selection effect is a central issue when we're dealing with observational data economics. Okay? All right. So some more definitions, and we are done with the RCM. So like I said the last time, the RCM, or the potential outcome framework, is just one framework that we will discuss on causal inference. We're going to be talking about another framework very soon, but just some more definition from the RCM. Okay? In RCM, we say, now if x is randomly assigned, then x is independent from the potential outcomes, from y0 and y1. Okay? And this independence has a name for it. We call this exchangeability. Exchangeability. Right. So when we randomly assign x, we achieve exchangeability. That's definition. So under exchangeability, it's a good thing. Once we have exchangeability, then we can directly compare x conditional, y conditional x equal to 1 versus y conditional x equal to 0. And we get that from data. If we do not have exchangeability, then we are in trouble because we have the self-selection issue I was just talking about. Right? So then we're going to spend some time on how to do that. But exchangeability is the idea that x become independent of potential outcomes. Okay? Now we also say in this case when x is exchangeable, there's exchangeability, we also say x is what? We also say x is exogenous. Are you all familiar with this word? Right? So exogenous in the Rubin causal model simply means that x is exchangeable, or there's exchangeability of x and y0, y1. In other words, x is independent from y0, y1. In that case, we say x is exogenous. Otherwise, it is endogenous. Okay. All right. When we have random assignment, we have exchangeability. And when we have exchangeability, we say we can directly get causation from data. How do we get it? We can directly compare EY conditional x equal to 1 will simply be EY1. Okay? And EY conditional x to 0 will simply equal to EY0. This is true if x is randomly assigned under exchangeability. Now we also say, in this case, we say correlation is causation. Now remember a very famous word, that correlation is not causation, or correlation does not imply causation. Well, correlation in general does not imply causation, but in special cases, for example, like this, when x is randomly assigned, correlation tells you causation. Why? Look at this. What is this? This is simply correlation, right? EY conditional x equal to 1. This tells you the correlation between x and y. This is pure data. There's nothing causation about it. However, it can tell us about counterfactual outcome. So by comparing EY conditional x equal to 1 versus EY conditional x equal to 0, by comparing these two, we are actually talking about the correlation between x and y. But the correlation tells us about causation. EY1 minus EY0. Because x is randomly assigned. So if x is randomly assigned, and you see people who, if I randomly assign difficult tests to you, and I see people who receive difficult tests, okay, maybe go crazy, and people who receive easy tests are fine, then the treatment effect of tests making people crazy is a true causal effect, okay? And so that's both a correlation and a true causal effect, all right? Mathematically, we can write it this way. What is correlation? Correlation, when we say x and y are correlated, the mathematical expression is EY or PY, right? PY given x equal to a is different from PY equal to b, right? When there's correlation, these two do not equal. When there's a causation, then the probability YA is not equal to probability YB. The counterfactual outcome, the potential outcome are not equal. Now, random assignment makes this one equal this one. PYA equal to PY given x equal to a. So under random assignment, if you see a correlation exists, that will tell you that a causation exists. Okay? So under random treatment, random assignment, correlation implies causation. Okay. Now, the idea points to the importance of experiments, because only experiments you can guarantee this random assignment, right? With sufficient data, you cannot do this. So experiment becomes this very central way of achieving exchangeability and making the correlation implies causation. Later on, okay, we will discuss many methods we can use to find out such causation from observational data. But the underlying key idea is the same, which is in order to get causation from observational data, we need to look for cases in which the correlation tells us the causation. Okay, because correlation is all we see from data. The data only tells us correlation. It will never tell us directly causation. But we need to find out special cases in which the correlation will imply causation. And that's how we are able to get causation from observational data. Okay? Later on, we'll talk about that. All right. Let me skip these three. So the father of modern statistical causal inference statistics is the famous Ronald Fisher, right? R.A. Fisher. So R.A. Fisher is the father of modern statistics, and he has made huge contributions to causal inference from the statistical literature. In particular, he is famous for designing experiments, right? Using experiments to discover causality. And this is one of his most famous books, The Design Experiments. And it turns out that how do you design experiments is a huge literature. Okay, so there's numerous ways we can design experiments very efficiently. Not the topic of this course, but if you're interested, you can study that. Let me right now just give you several examples where, first of all, if we directly use observational data, we are in trouble. And second, if we use experiments, we can try to solve that. The first example is demand estimation. Now, you're all familiar with that, right? So demand estimation is I want to know the consumer demand for the particular product. Okay? Now, we know in reality, from your econometrics class previously, you have all studied that you cannot directly use P and Q to estimate demand function. Right? So you cannot just, P and Q, and you link it, it's a demand function. You cannot say it's a supply function or demand function, because every point is an equilibrium point, right? Okay, so I hope you're all familiar with that. The simultaneity issue in that, right? But let's try to put that in the RCM framework, in the Rubin causal model framework. So in the Rubin causal model framework, we can state the problem as we can think about the demand curve. What is the demand curve? The demand curve says if price is high, how much do you want it? How much do you buy? Price is low, how much do you buy? So I can think about this price as a treatment you receive, okay? So you receive the high price treatment or you receive the low price treatment. What will be your potential outcome? So the treatment here is price. The outcome is the purchase, the Q. Now, for simplicity, okay? For simplicity, let me assume there are only two price levels, high and low. Okay? Low and high. And I'm going to say for every person, there are two potential outcomes, QL and QH, which is, the purchase you will make if the price is high versus the purchase you will make if the price is low. So to know your demand curve is to estimate the causal effect of the price on the outcome. All right? In particular, I want to know the average treatment effect is the E QH minus QL, right? It's back to the QH minus QL is the treatment effect. And indeed, you can think about this as actually the demand curve that we are trying to estimate. All right? Okay, so what is the data? Well, the data is Q1, Q1, P, and QL. Question, can we directly get the ATE from the data, right? Can I do this? Can I say the treatment effect, can I say the ATE in this case is simply equal to the expectation of Q, the observed Q, conditional on P equal to H, P equal to L, right? Minus EQ conditional on P equal to H. Can I directly write this, right? Can I say because the AT is what? The AT is EQH minus Q, well, let's just L minus H, right? Because L tends to be larger. Okay? So can I write this way? Can I just simply, what is this? This is simply look at what people buy when P equal to low. Right, this is the actual price, right? When price is low, how much do people buy? Demand function, right? PQ, when P is low, how much do people buy? Something here. When P equals high, how much do people buy? I'm sorry. When P equals low, some people buy here, P equals high, here, right? If we simply compare these 2 points, okay? If we simply compare these 2 here, does it tell me the actual effect of price on people's purchasing behavior? That's the same question as asking. That's the same question as asking, can I think about these 2 points as a demand curve? All right? Same question. The answer is no. You cannot. In general, you cannot. Why? Because why we cannot do this? The simple answer is P in reality is not randomly assigned. But what is the problem of not randomly assigned? Again, what does random assignment achieve? Random assignment makes this treatment independent from potential outcome. So that's one answer. But the more straightforward answer is random assignment make the people who receive different level of treatment almost exactly the same. Okay, so once you have random assignment, people who receive P equal to L is just like the people who receive P equal to H. In that case, we can use this to infer the entire population. That's really the intuition. All right. So in reality, that's not the case. In reality, people who receive P equal to L may be different from people who receive P equal to H. Why? Think about it. When P equal to H, this is how much people will buy, right? When P equal to H. Oh, sorry. So when P equal to H, the people who will buy, are they the same as the people who buy when P equal to L? They're typically very different people. Okay. Especially when P equal to H, when price is high, the people who end up purchasing when price equal to high tend to be the people who have higher income. So the income level of these people are different from the income level of these people. So they are actually different population. So you're comparing the purchase of one population versus the purchase of a different population. And that's incorrect. Right? So income in this case is something that will make our effect, right? So will make our causal inference incorrect. People who choose to purchase when the price is high tend to be richer. And that is a self-selection effect. That people who choose to purchase when the price is low. So in that case, if you simply compare their purchases, right, the purchase when price is high versus purchase when low, you're not getting the true treatment effect. What we here truly want is how price change will cause a person to change his consumption. But if we're comparing rich people consumption versus poor people consumption, if we're comparing rich people consumption versus poor people consumption, we're not getting that. So in order to get the true causal effect, there are many ways to do it, but one way, simply straightforward way to do is to do randomization. Okay? Just we randomly give price, high price versus low price, to people, to random people. So that the people who receive the high price, who purchase when price is high, versus people who purchase when price is low are almost exactly the same group of people.
If the good is nicer, I mean, it's not affected by the income in this case. So
if the good is what?
Necessary.
Yeah.
Yeah.
So I mean the income, the demand elasticity is close to zero, right?
Yes.
Okay, so people have to buy it. Well, in that case, yes, you may be true that income will not be affected. Okay, so again, I'm not saying, so this is a good question, because I'm not saying that it's not a case that, I'm not saying observational data cannot be used to uncover the causal effect. What I'm saying is we need to find out situations in which the observed correlation will give you the correlation. So if you believe that the observed correlation is indeed the correlation, if you believe, for example, income has nothing to do with it, right? Everybody will buy anyway, so that it's no longer an issue, then in this case, the people who receive the high price versus people who receive the low price are almost exactly the same. Then you can directly infer the causality from the correlation. Okay, but in general, it's not the case. So that's why in general, we need to do something like experiments, right? So in reality, what can companies do? In order to find out the demand curve or the true treatment effect, what people can do is you can run experiments. For example, right, this is what companies often do, is they do A/B testing online. Right? So if you're an online company, then it's very easy for you to do experiments. You can just randomly give a random person high price versus low price. And you can see how that person responds. All right? Now, that person's income is not going to change from the time you give it a high price versus low price overnight. Right? So this is very different from reality. When if you do not do experiments, you cannot guarantee that these two people are the same people. But if you do experiments, then you can just give the same people high price with low price, and you see how that person responds. So A/B testing in reality is a very good way to find out the demand curve. So that's the power of randomization, if you will. In a famous experiment like given behavior, this is the famous experiments that I also talk about in my intro class, which is economic theory has long postulated the existence of something called a given behavior, where for very poor people, if you increase the price, they are actually going to purchase more of the staple food, or the staple good. There's something called a staple food, and when you increase the price, they actually purchase more. So the demand curve is upward sloping. All right, so that's a theoretical conjecture that has never been proved in reality before like 2008 or something. Okay, now in reality, what you often see is when price is high, people buy more. That's a very common thing. It's nothing surprising. In China, for example, our price is always, in China, everything has become more expensive over the last 10 years, and people are buying more and more. Right? So it's not, but are they telling, does this tell us the true demand curve? No. Why? Because our income has also become higher. Just like the story I was telling before, right? So compare today's price of 10 years ago, today's price is high. But we buy more than we purchased 10 years ago, right? Because our income is higher also. So when you compare today's purchase with 10 years purchase, it's unfair because you're comparing different kind of people. One group of people is richer, which is today's people, rather than the people 10 years ago, right? So you're not comparing the same people. In other words, the assignment, the price is not randomly assigned to the same group of people. Right? It's correlated with potential outcome. Right? Okay, so in that case, you cannot say it's the causal effect, or you cannot say it's the treatment, the true demand curve. So in order to find out the true given behavior, which is holding income constant, holding everything constant, just simply changing the price and seeing whether people will indeed increase their price when they are poor, will increase their purchase when they're poor, and when you are doing staple food, the way to do it is through experimentation. And that's what these two people did, right? So this is a very famous paper by Jensen and Miller, where they went to in 2005, they went to 2 villages in China, in Hunan and Gansu, where they actually did experiments, where just randomly give people different prices, okay, and let them see, observe how much they purchase, and they do observe given behavior in that case, which is very difficult to do from observational data, because observational data, like I said, has this problem where the X is now randomly assigned. Okay? Now, if you're familiar with the econometrics literature, you will know that what I'm talking about here is also exogeneity. When we randomly assign price to people, the price is exogenous. Okay? So in that case, you can infer causality from it. Now, if the X is self-chosen, like 10 years ago versus like today versus 10 years ago, where the people who receive the X are different people, in that case, the X is endogenous. In the language of Rubin causal model, endogenous means the X is correlated with potential outcome. Exogenous means they're independent. Okay? And experimentation ensure exogeneity. Okay. So some more examples, right? Now in economics, in applied economic research, program evaluation is a huge literature. In economics research, we're often curious, right? We often care about things like the effect of policy on certain things, like the effect of worker training program on employment, the effect of early childhood education, intervention on adult outcomes, the effect of income tax or negative income tax on labor supply. Right? So we have all these effects of government programs we're interested in. In fact, we call this entire literature program evaluation literature. Right? So that is large literature in economics. Oftentimes, when we want to find out the true effect of a program or policy, the best way to do oftentimes, is also through an experimentation. Okay, so when you can do randomized experiments, you go and do it. It will, because randomized assignment tell you the true, because random assignment makes sure that correlation implies causation. And doing randomized experiment is often an effective way for us to find out the true causal effect. So this is a very famous example of true randomized experiment run by the U.S. government in Tennessee. So the experiment is about classroom size and student learning. Now in education, not in economics, but in education, people are often curious about when a small class makes students learn better, right? Do kids go to small class, how much does it improve their performance? Okay, the question is, can you directly compare small class performance versus large class performance? Can you directly compare that? You cannot directly compare that because the assignment of, in this case, you can think about the classroom size as a treatment. So X is the classroom size, and it's a treatment that we give to students. Now the problem is this treatment, if not randomly assigned, can often be correlated with potential outcome. Why? For example, kids who are typically who are the kids that have smaller class? Typically rich kids employed in not employed, but rich kids going to private schools. Who are the kids that go to large class? Poor kids in public schools in the US. So if you directly compare them, that's unfair. Again, they are different kind of people, and their difference is correlated with their potential outcome, which is their performance, okay, under different regime. So in order to solve that problem, we can do randomization, so, which is we take the same group of kids and we randomly let these kids go to a small class, and randomly let those class go to bigger class, and we compare the difference. In this case, randomization makes sure that the kids who go to smaller class versus large class are almost the same kind of kids. Okay, they're almost the same people. So in the end, if you compare the difference, the correlation tells you the causation. So, right? Okay. So that's exactly what this experiment did. In 2002, the U.S. government basically did this called the Tennessee Star Project, where they go to Tennessee. Right? People know what Tennessee is, right? Okay, I hope. Well, if you've never been, it's no problem because it's not a place that's very fun to visit. But anyway, so Tennessee is a place where you can go. Tennessee is a place where the project is done. And they randomly select a cohort of students, kindergarten, very small kids, and assign them to 3 different groups. Small class, regular class, and a regular class with a teaching aid. All right? And the experiment ran for 4 years, involving a total of 10,000 kids from 80 schools. So extremely large experiment, okay, very large scale, involving almost all the public schools in Tennessee for that age range. And the results is analyzed by Alan Kruger, the very famous Princeton labor economist, who unfortunately passed away recently. Right? So Alan Kruger analyzed the result, and here's the result. Okay, so this distribution is the distribution of regular small class, and this is the regular class. And because we follow them for 4 years, starting kindergarten, we follow the first year, second year, third year, we follow them for 4 years. We can see that small class is the black line, right? Small class kids consistently have higher grades than regular class. Right. Now the difference is what? What is the AT? The AT is the mean of the small class minus the mean of the regular class. But if we do not look at the mean, if we look at the entire distribution, we can see 2 things. First of all, we can see that the distribution highly overlap, right? And the second, so the difference is really not that huge if you look at the distribution. However, there is this difference in distribution, which can be captured by the AT, the mean in that difference. All right. So the small class does have some effect, maybe not huge, but does have some effect on the performance of kids. All right. And this difference tells you the causal effect. So that's the key. Without randomization, the difference does not tell you the causal effect. Okay? Because kids, without randomization, again, the kids who take the smaller class are different from the kids who take the bigger class. And the difference can be correlated with potential outcome. But with randomization, you can think about them as the same kind of kids. So you can directly compare the difference. The correlation tells you the causation. So, right. So, and there's some statistics you can read from the paper. If you're interested, I'm going to talk about them here. The conclusion of this paper is this. According to Alan Kruger, if we directly use observational data, compare people from large class with kids from small kids, we will conclude that large class actually work better if you use the observational data that they have. But if you do experiments, it's clear that small class outperform large class. So small class does have this positive causal effect on student learning. Okay. All right. Okay, so this is so far the example I want to give on the virtues of experiments. Right. So far I've been talking about that experiments is an effective way of discovering causal effect. Because experiments, by randomly assigning treatment X, make sure that the people who receive X equal to 1 are similar to the people who receive X to 0, so that X become independent of the potential outcomes, or in other words, X become exogenous. So in that case, the correlation will imply causation. So that's all I'm saying, right? Experiments is a good thing. However, for the rest of this class and the next class, I will talk about why experiment is oftentimes not a panacea and oftentimes lead to a lot of trouble. Okay? Especially I will talk about why experiments like this actually may not tell us anything about the underlying true causal effect. Okay? So let's think about it. It seems that the experiment is successful. It tells us that small class has this effect, more effect than large class, regular class, and it tells the causal effect. But let me just ask you, what causal effect is this? What is the causal effect that is being uncovered by this study? Does this study tell us that small class is better than regular class? It seems that this study does, because we randomly assign students to class, right? And small class perform better. So, can I trust this study and I say, okay, small class is better. Let's do small class in China. Let's do small class in Chicago. Let's do small class in Africa. Can I do that? So in other words, this is an experiment that's done in Tennessee. Okay, in Tennessee, 80 Tennessee schools. And we discover from this experiment that small class is better. From this experiment, okay, small class is better. Does the causal effect hold? Can we say the same causal effect exists if we're not in Tennessee? If we are in, for example, if we're in urban Chicago, where a lot of schools are black kids. Now here in Tennessee, if people have not been to Tennessee, once you know that Tennessee is a white dominant suburban area. Does the same effect that exists in the white suburban area exist in the dominantly, for example, black low-income area in Chicago? Does it apply? That's the first question. The second question is, does the same causal effect exist in China? Can I say, okay, based on study, small class is great. Let's do this in China too. Can I say that? Okay, or let's be more fancy. Can I say the same effect exists in Hogwarts or Harry Potter and his friends? Is it true that small class is better for those kids? Right? Can we say that? Can you say that? Based on the experiment done in Tennessee, can we say universally that small class is better? Now, the easy answer is no, you cannot say that. You cannot say that. Because why? Because the people are different, right? So the simple answer is people are different. Because the people in Tennessee are white kids, majority white kids, suburban area of a certain income range, and a certain, right? And so it may not apply. It may not apply to Chicago, where, in the black neighborhoods, it may not apply to China, where a completely different kind of culture and teaching method. It may not apply to, certainly may not apply to Hogwarts and Harry Potter, right? Okay, so that's the easy answer. But the difficult answer is, then what is this study about? If this result doesn't apply, then what is the study about? And how do we apply any result from experimentation to anything? Now that's the hard question. Okay, so I'm going to spend some time on that hard question. But let me just okay. So even if we say, okay, this experiment doesn't tell us about Chicago, doesn't tell us about China. Let me ask you, does this experiment result apply to Tennessee? Can I at least say that this experiment tell me that the small class actually works in Tennessee? Or maybe works to these kids? Can I say just the experiment tell me that small class is better for these kids? Can I say that? Even that, we may not be able to say with confidence. Why? For example, this may be the first time these kids ever participate in this kind of experiment. It may be the first time that some of these kids actually have a large class. Okay? Because kindergarten you used to have small class, and then when you go into kindergarten, you give large class to some people, you give small class to other people. It may be because the first time when kids sit in a large class, they are not, they are not accustomed to that. Maybe after a year they become accustomed, then their performance become the same as the people in small class. Maybe that's a possibility, right? So that if you do the same experiments on these kids again, the effect may disappear. It's totally possible. It's completely possible. So the estimated treatment effect may not even apply to the same group of people, not to mention China or Africa or any country. Okay. Right. So really the interesting question is, what actually can we learn from the experiments? And where do the experimental results apply? Right. So here's the answer, right? I'm not going to... the answer is, in order to understand what an experiment truly tells us, we have to know something. We have to understand something about the underlying mechanism, the causal mechanism. Experiment is not a way for us to avoid thinking about the underlying mechanism. Only when we understand the underlying mechanism do we know what the experiment truly tells us and where the effects may apply. Okay? So let me be more specific, all right? In this case, we're interested in the causal effect of small class on performance. But before going out to do experiments and estimating the effect, first ask yourself, why would a small class work? What is the mechanism? What is the mechanism that small class may improve student learning? What is the possible mechanism? Okay? If you understand if you have an understanding about the mechanism, then you know what the estimated effect from experiments tell you, and you know how widely it may apply. For example, okay, suppose based on our understanding about education, we know that the only way that small class helps is because people sit closer to the blackboard. Okay, suppose that's our understanding about the mechanism. So the only way that it helps is because people sit closer to the blackboard. Now, if that's the case, then based on this understanding, can we say that the effect estimated from Tennessee also works in China, also works in Chicago? In that case, yes, we can. Because in China and Chicago, everywhere in the world, smaller class means sitting closer to the blackboard. Correct? So if sitting closer to the blackboard is the only mechanism in which small classes help, then from this experiment, we can confidently apply the results to everywhere in the world where small class matters, okay? Where people sit closer to the blackboard. The only place we cannot apply this result is Harry Potter and Hogwarts, because in that case, people do not use a blackboard for teaching, right? Okay? Now, so this may sound like a joke, but the point is, understanding mechanism helps you understand where the effect applies. It's very important. Now, on the other hand, if you believe that the way that small class influence student-teacher has a lot to do with the methodology that teachers use. So, for example, in Tennessee, maybe it's the case in Tennessee, or maybe in America, that teachers use a lot of interaction. Okay, a lot of teachers talk to students a lot. There's a lot of small group discussions, right? The teacher really like to interact with students. So in small class, it's more convenient for teachers to interact. In large class, it's harder for teachers to interact. So if interaction between teacher and students is the mechanism that small class improve learning, then the estimated causal effect from Tennessee may not apply to China. Because in China, teachers may not interact with students, the teacher method is different. Teacher may like to lecture, like what I'm doing, right? We're not doing a lot of interaction. Okay? So that's a Chinese way to teach it. So in other words, if this is the mechanism, then whatever we estimate from Tennessee may not apply to China, because people use different teaching methods. And it certainly doesn't apply to Hogwarts again, because again, the teaching method is completely different. Right? Okay? Right, so the point, again, here is understanding mechanism allows us to say what this causal effect actually means and then where it actually applies. Without understanding the mechanism, then the experiment is almost meaningless. You can do the experiment, you can estimate the effect, but you have no idea what this effect truly means, and you have no idea where this effect actually applies. Okay, so that's really the idea what I'm trying to discuss here, right? Okay. So in summary, right? We say that causal effects do not exist in a vacuum. Right? Any causal effect belongs to a certain. Especially in social science. In social science research, the causal effect we're interested in is often the result of a very complex social and economic process. It's not a simple thing. It's not it's very complicated. Behind every causal effect, even as something as simple as small class, there can be a lot of complicated process going on. Small class effect can be, the effect of small class can depend on distance from blackboard, teacher interaction, teacher methodology used, student interaction, right? All these things can change the effect of small class on students, right? So it's very, very complicated. So in that case, every causal effect is often population specific. By population specific, I mean the causal effect of X on Y is always with respect to a certain population. And that population is also always in a specific social, cultural, and economic environment. Okay, it's not isolated. All right? So anytime when you say the causal effect of, let's say, small class on learning, you're really talking, you have to be more specific. Are we talking about the causal effect of small class on learning in a certain population, like in the Tennessee population, where the teaching method is this, where the student culture is this, where et cetera, et cetera, et cetera. So under many different cultural, social, economic environment. All right? And I'm also going to define a concept called scope. So scope is the set of population. Okay, oftentimes causal effect is population specific. And then we say the set of populations in which a causal effect applies is called the scope of the causal effect. Okay? The scope is how widely or in how many populations a certain causal effect actually is true, okay, holds. That's called a scope. So a causal effect, my message here is a causal effect is only meaningful if we can define its scope. If you cannot define the scope of a causal effect, meaning you do not know where the causal effect applies, then the causal effect is almost meaningless, right? Okay? All right, so how do we know the scope of a causal effect? We have to, again, understanding the mechanism. But let me go back to, I'm probably running out of time. Let me go back to an earlier point, which I have already skipped. Okay, so let me come back to the early point, right? So I want to before discussing causal effect and its scope, I need to talk about something that I didn't discuss before just now, but I need to define it. Okay, so remember that in doing randomized experiments, we can randomly assign X. And then we can compare the Y, right? So that's the way random experiment is done. Now, in reality, oftentimes there are other variables you want to control when you do random experiment. So what do we mean by control? We mean we fix the value of something, and then we do random experiment, and then we fix the value of variables to some other thing with the random experiment. Example. Suppose we are interested in so suppose we're interested in the effect of a certain fertilizer on a crop, right? So if I do this fertilizer, how much does the crop grow? Well, we know that the performance of the fertilizer is influenced by temperature. When temperature is high, the effect of fertilizer is this. When temperature is low, it's another effect, right? So in other words, the causal effect depends on the temperature. So in this case, how do we do the randomized experiment? One thing we can do is we want to fix the temperature, okay? Fix the temperature to high, just only in hot days. In the summer days, we randomly assign fertilizer, see what the effect is. And then when the weather is cold, we randomly assign again and see what the effect is. In other words, if temperature changes the causal effect, then in random experiment, in order to get the true causal effect, we can fix the temperature, okay, conditional on temperature, and then do the randomization. If we do that, that's called a conditional random assignment. Okay, it's not total random, it's conditional random assignment. And the conditional random assignment achieves conditional exchangeability. So let this S be a variable like temperature that changes the causal effect. Okay? So we do conditional on the value of X, meaning we fix the temperature, and then we do randomized experiment, okay, random assignment. The result of this is X become independent of potential outcome after conditional on S. Okay? Conditional exchangeability. Okay. So Now, we give this S a name. In experimental design, this S is also often called a nuisance factor that you need to control. But this is not important, okay? The name I want to emphasize is this S is often called the effect modifier. The effect modifier means this variable, like temperature, will change the causal effect. So the causal effect will be different, depends on the value of S. In that case, we say S is called an effect modifier. In the example I just gave, the causal effect of fertilizer on crop yield depends on temperature. Different temperature will have different causal effect, right? So in that case, S, the temperature, is a effect modifier. Okay. All right. Now, similarly, if I want to say, okay, I give you this drug, and how much does this drug improve your health? What is the effect modifier? Well, gender is typically effect modifier. Men and women, when they receive the same drug, it may have different causal effect. So gender is a effect modifier. So anything that changes the causal effect that we're interested in is called an effect modifier. Okay, so I think that's an easy way to think about it. Okay, all right. So now let's go back, right? Let's come back to the discussion we have. Now consider a binary treatment X, meaning X is 0, 1. In a specific population, causal effect only exists within a specific population, right? So in a specific population with a specific social, cultural, and economic environment, what is the causal effect we're interested in? That's EY1 minus EY0. But I can always write it as this, okay? I can write it as so this is the population, okay, I'm interested in. So I want to know what is what is Y1 minus 0 in this population. But I can always write this as the distribution of Y1 minus Y0 conditional on S. This S is effect modifier. Okay, anything that changes the causal effect. This S and PS, the distribution, okay? I can always write it this way. What I'm saying here is the causal effect that exists in this population, the mean, the average causal effect, the ATE, is actually a function of the distribution of the effect modifier. All right? What is it, so to make it more concrete, the effect of a fertilizer on a certain crop. Okay, so if we're looking at if I randomly give fertilizer to different crops, and I look at the yield difference, the yield difference depends on what? So suppose temperature is a effect modifier. Then the difference, the ATE, depends on, in our period of study, how many days are hot and how many days are cold, right? If our study is done in a period in which every day is hot, versus a period is done in which every day is cold, we will get very different ATE. So the effect, the final ATE, the average causal effect depends on how the effect modifier, anything that can change the causal effect, how the effect modifier is distributed in this population. People clear? Or if I want to know the average treatment effect of a drug on people's health, and the drug have different effect on men and women, then our ATE, computed ATE, depends on how many men is in this population versus how many women. So it depends on the distribution of the so-called effect modifier. So that's the first point. So the second point I really want to make here is the causal effect of X on Y can differ between two populations. Two populations have very different ATE. Okay? And this difference depends on two things. The first is the distribution of the effect modifier is different. So one population has more men than women. The other population has more women than men. And will give you a different ATE. Or one population has more hot days than cold days, the other population has cold days than hot days, it give you a different ATE. Right? But there's another reason in which the ATE will be different. The causal effect will be different. Which is the mechanism also different, right? Okay? The mechanism between the population can be different. So let me give you an example. Okay? So the reason why this can be different in different populations. The first reason is the causal effect, the causal mechanism is different. Example, the effect of decreasing oil supply. Suppose we're interested in if I decrease oil supply, okay, how much does the effect on gas? So suppose this year we're not producing a lot of oil. what is the effect on the price of gas? Now I'm going to compare this effect. So this effect totally depends on what? Totally depends on the economy I'm looking at. Suppose I look at two economies, in which one economy the gas price is in free market determined. Okay? It's completely free market determined. Versus another economy in which the gas price is completely regulated by government. Right? Then decreasing oil supply or changing oil supply will have very different effect on gas price in economy A versus economy B. Right? Okay? Because economy A is a free market, economy B is government regulated. So in other words, the mechanism is different. So the same causal effect, right? The causal effect of X on Y can be different in population A versus population B because the mechanism is different in population versus population B. The second case is the mechanism is exactly the same, but the effect modifier is differently distributed. That's also a possibility, right? So example, the impact of raising the retirement age. Okay, so if I raise the retirement age, what is the impact on the economy? Now, and I'm going to compare two economies that are very much alike, but however, they have different distribution of age. So if I compare Japan versus America, then Japan has many more older people. Okay, so the age structure is different. So then raising the retirement age will have a different impact on Japan versus the impact on the US. The causal effect will be different. Not because the mechanism is different. The economic mechanism can be exactly the same, but the distribution of the effect modifier, in this case age, is different. Right? Because age clearly has something to do with, right, just the effect modifier, it changed the causal effect. Okay, so what is the lesson here? Well, okay, actually, before talking about lesson, more definitions. I'm going to say an experiment of all observational data is always conducted on a specific sample drawn from a specific population. I'm going to say the population on which the experiment is done, or the observational data, where the data come from. I'm going to call the population where the study is done. I'm going to call it the study population. Right? But oftentimes, we're not interested in the study population per se. We're interested in a target population, which is we're interested in using the causal effect on another different population. It's like I'm doing a study on Tennessee, but I'm interested in what this can tell me about small class in China. So in this case, Tennessee is the study population, and China, or any city like Xiamen, would be the target population. All right? Okay. So the result of an experiment or observational study, we say the result from that study has internal validity if it is true for the study population. So the Tennessee study, the study conducted in Tennessee, may be valid for the Tennessee population. In that case, we say it has internal validity. Now, we say it has external validity if the result can also be applied, generalized or extrapolated to other populations. Okay, so if the study result from Tennessee also applies to other parts of the US or other parts of the world, we say it has external validity. The ability to be extrapolated from one population to another is called the transportability of a causal effect. If a causal effect estimated on one population can be used in another population, we say the causal effect is transportable. Okay, there's a transportability of the causal effect. All right. Now, finally, a causal effect that we have learned is transportable if what? If the causal effect is transportable from the study population to the target population, it must be because the study population and the target population are both within the scope of the causal effect. Remember the definition of scope. The scope is the total set of populations in which a causal effect can be applied. All right. So only if both are in the scope of a causal effect, the causal effect has transportability. So here's the punchline of today. All right. I hope. Obviously, our class time is limited. I cannot really go into more discussion about the examples I gave today, but I hope you go back and review the slides. But the punchline I want to say today is this: in order to understand the meaning, the meaning what the causal effect says, and the scope, meaning where the causal effect can apply. In order to understand the meaning and scope of causal effect, the key is we have to understand the mechanism. We understand that what is the mechanism in which we have, by which we have this causal effect. Only then can we determine what is the scope. Remember, the causal effect can be different in two populations for two different reasons. The first reason is the mechanism is different. The second reason is the distribution of so-called effect modifier is different. In order to know, so if you're trying to get your causal effect from your study population to a target population, you need to do what? You need to make sure that the study population and the target population, number one, have the same mechanism. Number two, have the same distribution of effect modifier. Only by understanding both can you make sure that you can use the causal effect from one study and apply to another population. Right? So understanding mechanism is key. All right? But where does the understanding come from? Where does our understanding of mechanism come from? It comes from our prior knowledge, unfortunately. So that's the key for all causal inference. For all causal inference, we have to base our results on our prior understanding. It doesn't come from the data itself. The data will not tell us. It has to come from our prior understanding. I'll talk more about this, where does prior understanding come from? I'll talk more about this next time, right? But here's the thing. So understanding causal mechanism is not only necessary for understanding causal effect, what it means, where it applies, but also for determining whether we can use a causal effect from one population to another, okay? And so it's essential in order for us to understand the causal effect. It is essential for us to understand the mechanism, right? So that's really the key. So back to experiments, right? For many people in econometrics, you will hear people, or statistics, you will hear people say that experiments or random experiments is the golden standard for causal inference. Many people take this to be, I don't object to that, but many people say this in a really careless way. They think that as long as I do experiments, random experiments, whatever I get is good. It tells me the causal effect, and I'm done. Now, such attitude is lazy, to say the best, okay? Because you can do randomized experiments. It can tell you you can then try to estimate something that's called causal effect. But you will never be able to understand the causal effect, and you will never be able to know how you can apply the causal effect, and what is the scope of causal effect if you don't spend time to think hard about the underlying mechanism. So without thinking about mechanism, even doing randomized experiment will get you nowhere. All right? And this is a key point of criticism, or key point of insight made by a very good paper. Sorry, I don't have it here. I'll show you next time. But the Nobel winner Angus Deaton, who has a very famous critique on randomized experiment approach to causal inference economics. And that is exactly the point that he repeated making that paper. All right, so we'll talk more about next time. I'm going over my time today. So we'll see each other next Tuesday. Okay?